Welcome to another episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor.
Welcome everybody again to another episode of our show, bringing another really awesome guest for you today. We have the honor of being joined today by Professor Dr. Afsaneh Rabiei, who is a professor of mechanical and aerospace engineering at North Carolina State University and a leading innovator in advanced materials engineering. She's also the founder and CEO of a related company called Advanced Materials Manufacturing. And Professor Rabiei is widely known for inventing composite metal foam technologies, this really interesting novel class of lightweight, high performance materials that ultimately combine exceptional strength, energy absorption, multifunctional capabilities. And her research sits at this really fascinating intersection of material science and mechanical engineering, and ultimately these real world applications with a particular focus on materials that can improve safety, resilience, performance in extreme environments. Professor Rabiei holds undergraduate bachelor's in science, material science engineering from Sharif University of Technology in Iran, went on to do her Ph.D. in advanced materials from the University of Tokyo, and then conducted her postdoc research at the Division of Engineering and Applied Sciences at Harvard. And over the course of her career, her research has been supported by numerous government agencies, including NSF, DOE, and Department of Defense, as well as various industry partners, ultimately focus on translating these fundamental material science discoveries into technologies with many applications: defense, transportation, nuclear energy, as well as space systems. And a lot to get into today. Very excited to have her with us. New topics we don't normally get into, but Professor Dr. Afsaneh Rabiei, thank you so much for taking time to come on the show.
Thanks so much, Ira. It was a long introduction, and I really appreciate it. Just call me Afsaneh, please.
Definitely. Yeah, no, I'm really looking forward to getting into a wide range of topics with you today. Would love to, start off sort of in the early days, and maybe starting off in sort of your early work in metallurgical processing in Iran, and then going to Tokyo, because I noticed your dissertation back in 1997 is on these very interesting aluminum-based composites, which is like, I guess, the early days of your thinking of metallic foams. But you introduce us to lots of interesting themes like matrix cracking and interface debonding and all the things that happen in these structures that ultimately deteriorate over time. But take us back a little bit to sort of your early days and what got you at least thinking of these really interesting ways to create new materials and make them ultimately more resilient.
That's a good question. I started my life as a metallurgist. I can tell you, when I was in high school, we had some site visits. We saw these companies who were kind of having this large, totally red hot pieces of I-beams and rolling and coming out of the furnace. And I was just there looking at it as a human, saying, wow, we get this, rock from the ore and bring it in and refining. And then look at that. It's so hot, we cannot even get close to it, yet it's under our control to build something out of it. So I was very impressed and intrigued with that. And I started my education in metallurgy and material science because of that. Early on, when I went to University of Tokyo, and I had the honor to work with one of the best professors at the University of Tokyo, or as Japanese call it, Todai. the metal matrix composite intrigued me again because you can combine two things and get the best of both worlds. In
Mm-hmm.
metal and ceramic, one is hard, one is ductile, and you mix those together, increase the hardness of metal and decrease the toughness, or decrease the brittleness of ceramic and increase the toughness by using a metal in combination. So it was nice. And when I went from there to work on metal foams at Harvard University, I get to know the benefits of metal foams and the shortcoming or the issues that are there with metal foams. And then coming up with the idea of how we can actually merge these two worlds of metal matrix composites and metal foam, that brought me up to the idea of composite metal foam, something that is porous but has a metallic matrix. So you have basically best of both worlds of metal matrix composites and metal foam. And I call it composite metal foam, simple and easy, right? So two things, you combine it, grab something from one name and the other and mix it together. And the concept is easy, but making it work was the different thing, right? So that become my challenge to see if I can make it. And this composite metal foam has never been made before. And unlike a lot of early students, when they come into the material science world, and they think that material science is like cooking, right? So you grab something and put it in a pot, and something else and put it in a pot and melt it together, and then that's the new alloy you make. Or I had some students, believe it or not, early on that they think that they can mix things together, which really is not the case. They start to learn that, oh, okay, so you cannot mix different materials and expect new thing happen. Sometimes you even end up having some exothermic reaction that can explode the lab. So I had to keep always warning them that don't do that. Don't try to combine things. But the longest story short, yes, the idea came from mixing these two material properties to come up with a new material that did not exist before, and offer some new properties that
Mm-hmm.
has kind of some good properties from this one, some good properties like lightweightness and
Mm-hmm.
energy absorption from metal foam come together with the strength and higher toughness of metal matrix composites. So you combine this together and create this new material. And early on, my job was to make it work. So to make it that in a way that it does show benefits, show properties better than the original metal foam.
Mm-hmm.
And once we get to that point, then, okay, where we can use it, what are the properties, how we are going to put these properties in the best use. That was the next challenge. And in the last 20 some years, that has become my challenge to make it work, to put it in the right use. And oftentimes I take it somewhere and test it, and the material surprises me every time. And it's, oh, I didn't know this, properties can be like that. And most of the times I'm pleasantly surprised, to be honest with you.
Yeah, I mean, it's again, and we'll be getting into some of the applications that you've worked on and seen translation in the field. Before we get there, though, I would love to, if we could just take a couple minutes, strictly from sort of a physical science perspective, and just let's get rid of the composite metal for a moment and just talk about foams in general, because we're all familiar sort of with these structures. I mean, we see them in the natural world in terms of coral and wood, and our bones are made of spongy foam-like material, but we don't fall apart. I mean, they have these really interesting properties, and sort of reading up ahead of time before talking with you, a major part of this is it's a lot less in terms of what these materials are made of, or that's important, but the geometry, the topology, ultimately how things link together that make things extremely powerful and elastic at the same time. Introduce us just to the physics of foams, if you would, and why they're so interesting from just a perspective by themselves, and then we'll move into composite metal foam.
Sure. So metal foams is less known compared to polymer foams or some natural foams. So if you look around, we have a lot of natural foams, right? So like you mentioned, our bone structures, skeleton, everything is porous. Even our skull that is kind of protecting our brain. And other type of foams, when you look at the grass, for example, it's porous and you step on it, it doesn't break. So that is the porosity and the kind of flexibility that the material has. In tree trunks, even birds, like for example, birds can fly because their bones are so porous and the structure help it to be lightweight and allow them to fly. With lower amount of energy, right? So then you think about man-made foam, right? You come from the natural foam into the man-made foam, and you see, for example, styrofoam. You carry this hot beverage in a styrofoam. It's lightweight and it can protect against extreme heat, so you don't burn your fingers. You talk about the bubble wrap. We always, send our gifts and delicate items wrapped in a bubble wrap. And that same concept can come into a metallic shape, right? So imagine that now you have a metallic sponge, a metallic bubble wrap, and that's what I've been working on. When I went to Harvard University back in 1997, after my graduation, I started learning more about metal foams, and that was the first project I worked on. And while working on metal foams, I realized that the manufacturing methods for these metal foams are not controllable, meaning that there are two types or maybe three main type of manufacturing. One is just you mix something together with some foaming agent. This foaming agent work like this material you add to the, like baking soda, you add to the cake batter, right? So you put it in the oven, and then this decomposition of those baking soda and reaction create this foamy cake or bread or something. Same concept in metals. There's elements like titanium hydrate. You mix it together with the metal powder or molten metal. And then at certain temperature, the titanium hydrate decompose and create this hydrogen, and hydrogen bubble into the molten metal or metal powder. As a result of that, you will end up having a metallic foam, but that foam you have no control over those porosities. It's like, can you control the bubbles in your bubble bath? You cannot, right? So the bubbles raise up, they grow, they kind of coalesce together and create larger bubbles. You have, even if you keep this metal inside a mold, they kind of rise up and reach to the ceiling of a mold and start to burst. And you see that these corners have very small, porosities. And then at the center where the bubbling starts, you get large porosities. And all of this porosity inconsistency will translate into unpredictable properties and even premature failure of the material. And that's what my observation was. Imagine you're a postdoc sitting in front of this machine, and it's kind of constantly applying this deformation load to a porous material. And you see, I can see that this particular bubble that is larger deform first. And then the rest of the bubbles go like a domino, because this bubble deform first. Now, if you look at, like, for example, if you have two rulers, one taller and one shorter, and then you apply force to it, the taller bubble start to collapse or buckle sooner, right? So that same concept goes into this structure made of, we call it a strut, this kind of cell walls that goes under the hood. And then the large cell buckle faster, similar to the ruler, right? The taller ruler. And so I thought, well, once that one bubble collapsed, all the little bubbles around it collapse right away. And that become like a domino effect. Um, and I thought, okay, so the solution is to remove non-uniformity. But how do we do that? Because the process of foaming is so very dynamic. You cannot control the release of gas inside the metal. Then there are other types of metal foam making where you actually inject air into the molten bath of metal. And that's exactly like a jacuzzi, right? So you inject air into the jacuzzi and it starts bubbling. And again, that's yet another way of making metal foam, which is not controllable as far as the porosity size and everything. There are other ways of controlling the porosities where you have a kind of negative of something, and then you pour around it, and then you remove that space holder by different ways. We have all different ways of chemical removal or burning and leaching and those kind of things. But then you end up with open cell metal foam. Just to step back a little bit, we have two types of metal foam. One is called open cell metal foam, where you have this ability to pass a water, air, or some sort of media through the porosity. And that's why it's called open cell. And there's another type called closed cell metal foam. And in that case, the cells are not interconnected. So if you try to pass like shop air, just or water through the porosity, you cannot. So that's called closed cell. Generally speaking, open cell metal foam is good for heat exchangers. So if you want to pass something through the porosity, that's good. Closed cell metal foam is good for impact energy absorption. And so if you want to protect, like a bubble wrap, right? So again, none of these methods were good enough for creating a uniform structure metal foam. I can show you something here.
Sure, please.
Magic box. So this is an open cell metal foam,
Okay.
The porosities are pretty open, and you can pass air through it. And definitely this is not something that you want for you to absorb impact because it's pretty weak. This one is a closed cell metal foam. You see that see if I can get it in focus. Okay.
Okay.
Yeah. So this one is porosities are not open to each other, right? So, if you try to pass air through it, it doesn't allow. But both of these being foam, they're lightweight and they are having different applications for each one for itself. Then the challenge that I had for myself was that how can I make it a strong metal foam with uniform cell structure and not really jeopardizing all other properties. So I hope that introduction on metal foams are not too much, but
no. It's fascinating, and again, you're just to sort of sum up some. I mean, there's a lot there, but moving from the gas created pores to these engineered hollow spheres, no longer thin and fragile walls, but thicker load bearing capability. more damage tolerance, better structural performance, and then so I mean, sort of looking through a lot of your publications, I think you present, I guess, the sort of the birth of this at this stage in a 2005 proceedings entitled "Processing and Development of a New High Strength Metal Foam." This is 2005. Talking about a lot of what you just went through, and we'll put a link to this paper as well as all your papers actually. But take us then, because they were around 2005. Then take us now a little bit, because from there, you continue working on improving, but the thinking of, okay, the multifunctionality of what we can do with this stuff, from ballistic resistance, blast mitigation, and everything else, where you go next. What happened after that? Sort of what happened between then and then some of, as I mentioned, some of the partners from DOE, NSF, and so forth. What happens next in sort of the development, the translation of what you were just showing us to scaling up, let's say, for some of these rather unique applications of the technology?
Yeah, so once we come up with the idea of making composite, making something that is a basically combination of metal matrix composites and metal foam, the next step was to, okay, we need funding, right? So I wrote proposal to the National Science Foundation, and I was lucky enough to receive a funding. In 2002, I submitted the proposal, and in February of 2003, I received the Carrier Award, which is one of the most prestigious awards from, nationwide, and particularly from NSF. So as it shows, it's Carrier, it's kind of, you initiate your career with this Carrier Award, and it was close to, was it 400,000 or something? Yeah. And then with that funding, we started manufacturing, and obviously not working the first time, the second time. So we kind of consistently improved the manufacturing, and we eventually came up with two techniques for manufacturing composite metal foam. One was based on casting. So we cast some material, molten metal, around the porosities, hollow spheres. And that looked like this one. So from an uncut surface that is like this, and when you cut it, it looks like this. And then we changed the gear to, in this case, we had to cast a molten metal that is having a lower melting temperature compared to hollow spheres material. So in this case, we have steel hollow spheres with aluminum cast around it. And it has its own challenges, like, how do we make sure that all those areas or spaces between the spheres are filled and not leaving any empty spots behind. And also to make sure that there is no intermetallic formed between the steel and aluminum and so forth and so on. The other technique that we had was based off of powder metallurgy, similar to additive manufacturing, which is based on making parts with metal powder. We had metal powder at that time mixed with hollow spheres, and that way we can make material or composite metal foam that has the same material for spheres and matrix. So this one is a composite metal foam that is made with steel spheres and steel matrix. So that is a cut section again, and here is an uncut section. So you can see the uncut section, the spheres are not cut, and the cut section shows that the spheres are. This two different methodology, we started patenting it. And honestly, at that time, as a young faculty, I was not thinking about entrepreneurship, making a company, or any of those. I thought that's cool to have a patent, right? So So we made it, and the very first time I announced the birth of composite metal foam, or CMF, was at MetFoam conference in Tokyo, or actually it was in Kyoto. And to be honest, I did not know it's a big thing until I went to that conference, and everybody were talking about this material, and some people were like even not happy that I patented this technology, and they were hoping that they would do it, and so forth. So I guess at that point I realized that, maybe I got something here, right? And then I started working on, now that we had the technology of making it, now let's learn the performance and properties. How is the material perform in different scenarios? How we can take benefit of the properties of the material. And that become the story of the next 2 decades.
Got it. Yeah, and when people get mad at you, you're on the right track, no doubt. But yeah, no, that's yeah. Let's go down some of these paths because again, each one of these projects it is equally, if not more fascinating than the next. And if there's anything you can't talk about here, just say I can't talk about that. That's classified or something. But I try to pull down as much of the publicly available info as possible, and I just think a really interesting place to start would be with the NC State's program with the joint aircraft survivability work that you did. And here, I'll let you run with this, but at the end of the day, whether it's an armored vehicle or an airplane or something like that, you were able to show that, these panels ultimately, and 50 caliber rounds, armor piercing rounds, absorbing something like 70% of the kinetic energy. So, I talk a little bit. I mean, I know about not much about sort of bulletproof vests and things, but when it comes to making an airplane or an SUV or whatever bulletproof or armor piercing round proof, yeah, I see the potential and why the DoD is so interested. Walk us through a little bit of the history of your involvement here and a little bit of what you found out.
Sure. So once we get to know the material performance and how it perform in absorbing the impact energy. First, we did just straight compression, and then we started hitting it with a high impact, and then we started seeing promising results. And later, the more I saw people coming back from Iraq who are injured, and especially the underbelly blast that at that time was a major threat for our troops, I thought, I wonder if this material can help. So I started looking into that, and especially it really hit me when I don't know if you remember, we had these beautiful, young soldiers, pictures you saw in the news, oh, this person lost his life here or got injured here, and you feel bad that, I'm one of those people. If I can help, is there something I can do to help? And if so, how I can help. And so I started with trying to write proposals to study the blast performance and see if we can offer this material as an alternative lightweight option for blast energy protection. And originally, before I start looking into the blast or anything, I started with lightweight material for accident protection, like in the crumple zone behind the bumper in cars, so that it will protect people, against potential injuries during car accidents. And then starting to look into this blast and ballistic. And I kept asking people how I can test this, where I can test this material. It's not obvious where you can test it, especially in a government lab. You can always go and do some testing in a private company, but that's not legitimate data. People can question that all the time. And for me, being a female in engineering who has an accent, taking this sample and then go shoot at my material. And people, yeah, sure. And I remember that I was introduced to a group at Fort Eustis to run some ballistic testing for me.
Sure.
And before that, I actually received a Chancellor Innovation Fund that was like $75,000 coming from the Chancellor's office, that you can get that. Don't use it for any salaries or student stipend or anything like that. Just go take your technology or invention to commercialization. At that point, we had inventions already patented or patent pending or something like that. So I got that money and reach out and then started to do some ballistic testing. One of the guys who was setting up my samples for ballistic testing told me at the day that I went there to test the samples for ballistic, he said, here we shoot at people's samples and hope in the same day. And I never forget that. And a nice guy, he later said, wow, you've got something. So I'm not shooting at your hope anymore. So by the end of that program, we had good results. And some of the folks over at Fort Eustis were interested enough to team up with us, and collectively we applied for the Joint Aircraft Survivability Program. That was not a big funding. It was just about $300,000, which was mostly used for the students' salary and tuition, things like that, to work with me in the lab and get samples made. And then I was going to Fort Eustis very early in the morning. They normally start at 6:30, so I had to leave my hotel before they start serving breakfast. And the place that we were shooting at the samples had no address. You had to just go by the coordination. And I was told that while you're driving past the gate, and then you'll see a lot of signs saying, do not pass, shooting in progress. Don't worry, keep coming.
Don't go there.
I was like really driving, like, okay, and I see people doing, shooting, practicing, and not that my life was in danger, but when you go there for the first time, you're kind of a little bit intimidated where you are, what you're doing. But it was a lot of excitement to see the sample in front of a bullet, and every time it just made me proud, and I just pray that the sample can survive. And we learned a lot during that program. And not only we tested the material against ballistic, we did ballistic like 7.62, which is, I think, 30 cal. And then we get the courage of getting it to 50 cal and even larger. And also we tested the material against blast. So in the case of ballistic, we learned that we need to put some kind of hard ceramic layer in front so that the tip of the bullet gets a little bit blunt. And then the rest of it is absorbed by the CMF. So think about it the way that if you have a bubble wrap and you poke it with a needle, it just poke the bubble. But if you poke it with something like a back of a pen, now you have a better energy absorption because the load is distributed over a larger area. So what happened with the ceramic face sheet is that ceramic face sheet is kind of blunt the tip of the bullet and spread the load over the larger area, similar to the needle as opposed to the back of a pen with the bubble wrap. And then the more larger area of interaction with porosities you get, the more energy absorption you get. So you need to get engaged more porosities to gain the benefit of that. Later, we learn that the faster you hit it, the more resistant you get out of the material. Meaning that when you hit CMF, this air inside each bubble compress. And when it compresses, it pushes back. It's exactly like an airbag in a car. So
Good.
the air pushes back, and then you press it more and the air pushes more. And then if you do it very, very fast, this air doesn't have room or doesn't have time to kind of dissipate through the material. It stays there and kind of resists. And the only way for the air to go anywhere and accommodate this fast compression coming from blast or ballistic is to burst the bubble. Now imagine that you have a metal balloon and you want to burst this metal. That requires a lot of energy as opposed to slowly compressing it. So we learned that in the case of ballistic or blast, it just hits so fast and the air inside react differently now. Instead of deforming this bubble, it kind of has to crack the bubble. Now, when one bubble is cracked, eventually after all of these forces, where the air goes, because imagine this is a millisecond or microsecond that is happening. Then the air has to go out, and as I showed you here, there is matrix between the porosities. It has to channel through the matrix, and that's the beauty of metal matrix part, right? So now it has to channel through the matrix to find its way out of the material. No, you have this air. It has to go somewhere in order to allow this deformation to happen. So if I show you one of these samples here, this is a sample that, shows compression.
Right.
Before and after. So this goes, and if you put it on top of each other, you see that it basically deform, and once it's deformed that much, the air inside has to go somewhere, right? And that's you said the physics. So there are two physics of metal foam here. One is the physics of making it, and one is the physics of how it works under loading or under different type of threat. Now we talk about the mechanical loading, whether it's blast or ballistic or impact, but also the performance in other kind of environment like fire and vibration and radiation, and those kind of things are different.
Let's let's go there next, because as you're outlining here, whether it's ballistic resistant or in the case of blast overpressure, why this is such a multifunctional material. But yeah, if we go to 2016, it's in the International Journal of Thermal Sciences. You publish experimental and computational studies on thermal behavior and fire retardant properties of composite metal foams. This is DOE funded. We'll talk about the radiation and neutron shielding in a little while, but let's talk about the thermal performance, because here again, I guess normally think about sort of metals being insulating, but again, you were able to show with these materials much greater insulation than, say, a solid metal because of this porosity. Obviously, a lot of applications there in terms of fire protection and other hazardous material work. Temperatures upwards of 800 degrees Celsius. Again, a really cool part of the story, and love to hear a little bit about your field work on this one and how you generate those temperatures in the first place and to study it for this.
Yeah, so again, every time we look into the properties, it's new. I was actually talking with one of my colleagues at my company who used to be my former PhD student. And we were talking about, he said, I'm very proud of the papers we published together because every one of those has a different depth and breadth. It just totally different. And you see sometimes people publish things and they're kind of similar in certain way, but in this case, we look at different properties of this material. And he was saying, like, every one of these is different and unique, and the first time. And that's true, because there's no composite metal foam. Nobody worked on metal foam to this point that we were doing in performances that we were looking at. Now, looking at the thermal, yes, there has been quite a bit of studies on other type of metal foams and their performances in thermal environment. But mostly they were like the heat transfer, right? And like I said, open cell metal foam mostly. What we did was looking into this composite metal foam, which is considered mostly a closed cell metal foam. It is not meant to allow filtration. So looking at the thermal properties of styrofoam, you see the air inside the material protect against heat. Even the air around the globe protect against extreme heat, right? So air is something that we take it as, granted and really don't consider much about, what are the benefits of that. Now put the air inside a styrofoam cup and you can carry hot beverages. Now, looking at the thermal properties of composite metal foam, you see that we have these chunks of air inside it. And when we look at the thermal conductivity, we saw that, the thermal conductivity actually is like 6-7 times lower than the conductivity of the parent material, right? So conductivity of steel as opposed to conductivity of steel CMF. Conductivity of even aluminum as opposed to conductivity of aluminum steel CMF. And the difference is huge. It's all related to the presence of air, because air is way less conductive than metal. And now that you have a mix of air and metal, and that air content will help protecting against. So the very first thing that we did was a project from Department of Energy to see if we can use this material for, say, transportation of nuclear material, nuclear waste transportation. And you see that kind of application require multiple kind of testing for certification. One of the testing was drop test, and we knew that, so CMF can absorb a lot of impact energy, so that's a given. But the other requirement was just fire test, where you have to expose the material against certain temperatures, up to 800, 850, and make sure that this material can resist the heat and not allowing heat to pass through. And at that time, we started to really learn about the thermal conductivity and insulating performance. In another project later from Department of Transportation, we look at the transportation of hazmat, where you have issues similar to we had experience in Palestine, Ohio, where this tanker carrying hazmat is derailed. And once it derailed, it kind of poked through with some woods or some other part of the system, transportation system. And this hazmat material is just spilled all over the place. Now that started the fire, right? And the other tank cars behind, they're exposed to that fire. So if the other tank cars are protected, then you're good. You can actually prevent a major catastrophic fire. And we have had some of those very catastrophic things in Quebec, like Canada, that created like 46 or something, 47 loss of life, and the entire city, like a small town, was burned because of the crude oil transportation. And one, again, one tanker caught in fire, the rest of those are like domino effect, all of the tankers caught in fire. So there are requirements for tanker for transportation hazmat that it has to resist fire up to 100 minutes against 870 or something.
Mhm.
And the temperature behind, so from one side it's exposed to 870 degrees C, and then from the other side after 100-minute exposure should not exceed 470 or something like that. 400, not 420. So the exact number is 427, I believe. So
Okay.
um
Pretty hot.
yes, and that's C, not Fahrenheit. And so we did that test, 100 minutes, piece of cake, we could actually not even exceed 400. So not only we didn't exceed 427, but also we didn't even reach 400. I think we were like the highest temperature I had at 375 or something. And you have to repeat the test 3 times. And after that, you have to do a torch fire testing where you need to expose it to 30 minutes to 1200 degrees C. And we did that, and we successfully have been able to do it on a 1x1 panel. And then later on, we had it for 4x4 panel. So in a nutshell, we tested the material against extreme environment of fire, of heat, of impact, of blast and ballistic. And every time it came out good. Now, I'm not saying that it's easy. It's definitely, there are failures. There are times that we have to go back to our notes and see how we can fix it, how we can do it better, how we can improve this or that. But at the end of the day, when you look at, I always tell my students that there's always failure. There's
Yeah,
always bad news and good news in life. If you
for
add
sure.
everything together and you are still in a positive, then you're doing good. But if you add everything together, cancel out the positive and negative, and you're in negative, then you have to think about, and a plan B.
Yeah.
So that's research, as you said, and yeah, I guess I
I
hope
mean,
that.
yeah, I mean, I come out of the drug development space, so I mean, yeah, it's all it's mainly failure until 1 out of 10,000 times. But no, again, I applaud these experiments, and again, some of the things that you're discovering along the way are just, again, point to that you've been on the right path, and just one other one I just have to ask you about because it's personally very fascinating. I mean, you mentioned before major catastrophes, and I'm sitting here in Philadelphia, and 3 Mile Island is just a couple hours that direction. But when that happened, yeah, it was it was kind of the end of the world. And in your December 2015 radiation and physics and chemistry paper, it's entitled Attenuation Efficiency of X-ray in Comparison to Gamma Ray and Neutrons and Composite Metal Foams. And you mentioned 3 Mile Island in the first sentence. this rang out to me. And again, if you could just talk a couple of minutes. So you've talked about blast and structure and extreme heat. Now we add in these high Z number materials like tungsten, which do amazing things to attenuate all sorts of nasty radiation. I mean, I guess you can't build me a nuclear resistant house anytime soon, but talk a little bit about what this means in terms of shielding for better nuclear power plants, for transportation. I mean, maybe you can build me a nuclear resistant house. I'd love that. But take us a little bit down this path. I'd love to hear this story too.
So for radiation, the concept was because we have so many interfaces of metal and air that can help to to attenuate some radiation, some vibrations and sound and those kind of different threats, right? And so I did not know whether or not we are going to get the right shielding that we are looking for. So we started with gamma ray, neutron, and X-ray. And again, we learn where the material perform better where it doesn't. Like, for example, normally for gamma ray and X-ray being a part of gamma ray, you need elements that are heavier, like we call it high Z, like lead, like tungsten and vanadium, and even steel to some extent. A lot of these nuclear structures are made of steel. And when you're talking about neutron, then you need something actually the opposite. So lighter elements like hydrogen and nitrogen and those kind of things. So thinking about composite metal foam being a combination of heavy metal and air being, hydrogen and nitrogen and those kind of elements. So you have best of both worlds together. If you can figure out the way to tailor it to the right capacity. So we thought, why not we get some higher Z elements, higher than steel, and then mix it together with the steel. Not the way I said earlier, not just putting in a pot and mix, but there was one steel tool steel that has a higher percentage of tungsten and vanadium, and those elements have higher Z compared to steel. So we replaced the regular stainless steel that we were using in the structure of CMF and put the high Z elements in it, or tool steel in as a matrix. And we made it and we tested that against gamma ray and even neutron. And the results were interesting because we didn't lose any of the mechanical advantages of the material, but we gained some radiation shielding better compared to the stainless steel. So we also have published another paper where we infuse the porosities of metal foam with some other elements that can further increase the radiation shielding. So depending on where you want to use it, we can tailor the CMF to that application. So if you are looking at using it to shield both gamma ray and X-ray, then you don't need to infuse the porosities. But if you only want to use it for gamma ray, then you may want to replace those or infuse the porosities with some other elements. And we had done that one as well. So the good thing about it is that tailorability, so you can tailor how much matrix you have, how much air you have, and what size porosities you have. You can tailor it as a functionally graded. Like if you look at your skull cross section, the bone cross section, you see that the outer layer porosities are finer, and then you go into the core, the porosities are larger, and then that is because the finer porosities have more material and more resistant. And then the farther you go into the thickness of the bone, the porosities size increase, and the percentage of porosity also increase. So we can do the same thing with CMF and have porosities controlled, the size of the porosities, the distribution of the porosities, functionally graded, straight, uniform. Can we do it like sandwich panel, put a layer at the top, at bottom, sandwich it, or bond it together with all sorts of different applications. And all of these translated into the question of, why don't you take it outside and make a company? And that conversation really started back in 2016. And people kept asking me, why don't you take it outside the university? And for the love of God, I never thought that I can do this. How people make a company, how to run a company. I'm a faculty. I have enough on my plate that oftentimes, my days are long, my nights are long, and now sometimes my students, I had one student came to my office and said, I want to fix your computer clock. And I said, it is fixed, you don't need to do that. Oh, but I receive a lot of emails from you at 1 a.m., 2 a.m., 3 a.m. And I thought that may be wrong. It's no, it's the time I send it to you. And I had been working really day and night, really long hours. And so with all of these, I didn't think that I can make a company, honestly, ever. And I never patented the technology thinking that, oh, I can be an entrepreneur, or can I be an entrepreneur? I'm not a business person. The only business I know is what I learned from my father. He had his own car dealership. And every now and then he sat me down to write his checks. And he always told me, oh, start from here, do this, and don't leave, empty spots ever on your check or something. And that was it. It was kind of very out of reach until I went to a conference and I met some generals, and I was one of the speakers and they were speakers, and I heard them say that we need things like this. And I thought, we have that. And I raised hands and say, okay, you need this, I had this. How do we pass through this valley of death and reach our technology to you guys, right? And I was fortunate enough that one of the generals gave me his card, and it was his personal card. And, me being a little naive, I thought, okay, we always exchange cards, right? But then everybody said, did he really give you his card? That kind of, yeah.
Wow.
So anyway, later, we had a visitor coming, and he spent the whole day learning about our technology. And he said, Dr. Rabiei, I showed him one picture. There is a poster in our department that is showing Wright brothers. One of the brothers is standing at the shore, and the other one is flying the airplane, and he's just maybe a foot or two above the ground. And that picture is always speaking to me, because you think about it, 100 years ago, we were there, and now we are going to Mars. And it really speaks to me. So I stopped in front of that poster in our department, and I showed it to him, this scientist also. And I said, that's where I am. And that's where we need to, from where we need to take off. And what I heard was that you need to take the technology outside the university and try to build it. You cannot just work with university research samples.
Sure.
And at that time, I bite the bullet. I said, okay, let's learn what to do. And that was the biggest challenge in life, to learn and to step in a position where I did not have too much education for it. My education is engineering, is research, teaching, mentoring, and my position as a founder and CEO at Advanced Materials Manufacturing was constantly on the job training. So I learned how to establish my company. I learned how to go from A to B to Z, and I'm still learning. So it's exciting and challenging at the same time.
Yeah, I mean that's the journey of an entrepreneur, and yeah, I mean yeah, we'll put the link to advanced material manufacturing in the show notes. But I guess you got a really cool logo as
Thank you.
well. But could you just again? I mean, and we'll link to this. You know, obviously a lot of service offerings from a lot of what we've just been discussing in terms of the military applications. But you got some stuff here in sporting goods and transportation and all that. I mean, maybe ask you just because I'm a life science guy, and I know you have some sort of bioengineering related patents and so forth in your portfolio. Any interesting stuff happening on the healthcare front? I mean, I know that's not part of AMM, but anything cool going on in terms of the healthcare industry that you can talk about, devices, biomechanical stuff that people may be contacting you about, or if it's secret, don't worry, you don't talk about it.
No, I mean, we have got some interest from sporting goods, like people reach out, you know, can we make a golf club out of it, or things like that. And I had to pick and choose what's my priority. And I will say, if I can save a life as opposed to saving an elbow, I prefer saving a life. So because time is limited, unfortunately. I only have 24 hours a day, and the farther we push my sleep time back and wake up early, it's 24 hours. As far as the other applications, like I said, radiation shielding is one area for healthcare. Another thing is a lot of devices like tools and vibrational tools that you consider, like the jackhammer or drills, and you know, people who are exposed to this type of vibration end up having something called hand and arm syndrome that
Okay.
actually create a lot of pain because of constant vibration. And the vibration is actually causing so many different side effects, from losing teeth to bone and to nerve damage and sometimes even death, believe it or not. So people reach out, and we are looking into like new devices where you can absorb the vibration, make devices lighter and more vibration absorbing. So from the radiation shielding part to the vibration absorbing, sound absorbing, and there is a lot of different applications. And sometimes people who are lifetime entrepreneur, they advise me that you need to go after the lowest hanging fruit, and just pick one application and just focus on that one. And I cannot do that because every day people reaching out and asking something totally different. And if I just focus on, say, defense, right? Then I close the door for transportation, I close the door for other things, then I'm going to miss some opportunities, and I don't want to miss any opportunities. And that's why I said, the lower hanging fruit is the one that shows itself. It's not my choice saying that, oh, I want to just focus on one thing. I want to keep AMM, or advanced materials manufacturing, at a position where it can decide this is a good paying customer, so I'm going to go after, or decide saying, do you want to focus on saving an elbow or saving a life? So AMM is a small business, and it has its own, manufacturing capability. And we came out of the university with literally this size manufacturing. And the largest we made at NC State was a foot-by-foot panel. At AMM, we have been able to manufacture 4 feet by 4 feet panels, and making it different shapes and sizes, round, flat panel. And we installed very large CNC machine, which is very, very unique in the area. There is no such huge CNC machine because we do need that for making our molds, making our samples. We have a robotic semi automated system for manufacturing, so I don't have to go and kind of manually make these samples anymore. And so all in all, we scaled our technology, and right now AMM is about 7,000 square foot facility with engineers and staff to address the needs of industry. And I'm very happy because in the past, I was the one who reach out to companies, reach out to people, say, we have this material, do you want to use it? It can offer this or that. And now people are calling me saying, we have this application, can you make a prototype for us? And I have the luxury of picking and choosing and who should I put as my priority and address their needs and make their prototypes to their application. So it's not one size fits all at all. We tailor for every application. And when people reach out to me, they say they have some original thought and they want it to be like this or that. But then I tell them that, based on my understanding of CMF, you probably don't need that big of a thickness. You probably don't need this. You're probably better off with this one. Do you want me to coat it based on what I recommend? And that way they oftentimes, I think so far, accept my suggestion, and we make the prototype based on that, and they test it, and if they're happy, then we go forward with bigger production. So that's where we are, the story from the beginning to where we are right now.
No, it's an awesome story. I love hearing not just great science and tech, but entrepreneurial journey as well. So I'm excited for you. Really am. Um, Before we wrap up, just Emma, we just stepped into 2026. What else is coming up that we should? I know that in a couple of months you're going to be in Rome at this global summit on civil structural and environmental engineering. Other public-facing initiatives, whether they're on the engineering front or on the company front, and then anything else I missed, what you want to mention while we have you today, please.
Well, I'm very impressed with all of your research. You've learned a lot about what we are doing, and that is very, very impressive. Thank you for all that. Actually, I had another conference coming up in Germany that had some conflict with the Rome conference. So I'm going to, and that's organized by Fraunhofer, and those are my friends who, I have a long history with. So I'm going to Dresden instead, and I had to unfortunately cancel my Rome conference. But this semester, I am on sabbatical from NC State.
Okay.
And 100% focusing on AMM to hopefully take this technology off the ground farther. And we are seeing good signs of interest from industry, focusing on prototyping and moving the both R&D and commercialization aspect of the material. So yeah, I am on sabbatical this semester working on CMF commercialization.
Yeah, again, as I said, I'm excited for you. It'll be fun to do a follow-up maybe next year to ultimately see the continued evolution of this. But it's just a really exciting story, and I just wish you and the team the best with it as you continue to move these very important tools on all these fronts forward, whether they're defense, whether they're industrial. Again, for everybody out there that's going to be listening to this episode, across the various podcast networks, or who will be watching on the YouTube channel. Again, you've been spending time with Professor Dr. Afsaneh Rabiei, Professor of Mechanical and Aerospace Engineering, North Carolina State University, founder and chief executive officer of Advanced Materials Manufacturing. We will put links to both in the show notes, but really impressive work on how you take these innovative materials, bold ideas, and ultimately turn them into these important solutions for society. But Asman, I want to really thank you for taking the time to walk us through everything that you've been involved in, educating us on some really unique topics that we don't normally get into. Obviously, thank you for everything you're doing for society and people via these applications. We like to say here on our show, thanks for helping to create a better tomorrow through the way you develop these technologies. Really, it's an exciting story, and I look forward to continue to follow you and the company.
Thank you so much for the opportunity. It's my dream to be able to save a life. I always have said that if one day I see that because of the technology that we develop, one person walk out of a deadly accident, whatever it is, safe, and we saved one life, then I would be, I think I left my mark. That's my dream, that's my goal, and I'm just pushing for that. Hopefully it will come to reality. But I really appreciate the time you spent not only today talking to us and hearing about our story, but also all the background research that you have done. I'm so impressed about what you have learned about our technology, what we are doing, and where we have come from, all the way from Japan all the way here.
Being a life sciences guy, I didn't want to sound like an idiot, so I wanted to make sure I did my research before I talked to you, and I try to hang in there with you as much as possible. But no, it's really a great story, and I look forward to continuing to follow it. It was just really great having you on the show.
Thank you so much. Same.
Actually, be well.
Take care.